Hello, today we will present our earthquake prediction models utilizing SVR and a neural network.
So for the background part, because everything happening with nature has tremendous impacts on human beings, earthquakes and natural disasters may take away countless people's lives, which brought up our attention. Earthquake prediction has been around for a while but has yielded no real success, and our group wants to work on this topic too at the very beginning of the project because I'm really interested in working with some sort of seismic waveform prediction and pattern recognition. We gathered together to form a group. We wanted to work on the time series data of earthquake forms, trying to predict how the wave may traverse to predict the earthquake severity. However, the data we could find online was not very ideal to predict that sort of waveforms. Fortunately, we're able to find a dataset that contains the date, time, latitude, longitude, magnitude, depth, and region of the earthquakes, which can be later visualized into a word map. The core components made us possible to work on the earthquake prediction model.
For our related works, we have included some similar projects and research articles we found useful when familiarizing ourselves with the topic. The first link is a paper that addresses our same problem. The libraries we use for the project include NumPy, sklearn, Matplot, TensorFlow, and Keras. For our data collection, we initially wanted to work with waveform data of individual earthquakes. However, the data proved to be difficult to collect and manipulate. We then shifted our interest to an earthquake's more general data like magnitude, latitude, longitude, and depth. The Incorporated Research Institutions for Seismology, or IRIS for short, host comprehensive data services on their site. Their Data Management Center offers an event list of recently recorded earthquakes from the last 24 hours. However, this event list is in tabular form and is not a CSV. In plain text, it looks like this. To comma separate the plaintext data, I wrote a script with a program AutoHotkey that would make the cursor traverse through the document, placing commas like so. Although this method works, it is quite impractical for the long term and for larger datasets. When trying to run our models on this data, it proved to be too small of a dataset to yield sufficient results. With some luck, I came across Iris's interactive earthquake browser, which displays events on a larger scale over a longer time frame. The graphic is also nice for visualization. Our final dataset is a record of 25,000 earthquake occurrences across the globe from September 25th to December 5th, 2022. It contains 10 columns labeled year, month, day, time, latitude, longitude, depth, magnitude, region, and timestamp.
Next, we have data cleaning. The original dataset had dates split up into separate year, month, and day columns, and it also recorded single-digit month and days as single digits. To make all the dates a uniform length, zeros were added to the beginning of these single-digit month and days. The year, month, and day columns were then combined into a single date column, and the former three were then removed. The original timestamp column was also removed, and the timestamp data you see in our model was regenerated by a function used on the date and time columns. And although we did not use the region data in our model, we decided to leave it in the data frame as a descriptor for the coordinates location. Here we have a visualization of the earthquake's coordinate data with a magnitude color map. In order to overlay the scatter plot of the latitude and longitude coordinates onto a world map, we used GeoPandas, which provided a data frame that would generate the map. Each dot marks the location on the map where an earthquake occurrence was recorded, and the color of the dot represents the earthquake's magnitude, with yellow to red representing low to high.
The methods we used in our project here is the first one would be a neural network with the parameters a batch size of 64, dropout rate of 0.5, neuron density level chose 32, and then the epoch size of 40. This is our baseline neural network. And then we ran a random search CV to optimize the hyperparameters. After running that, the random search came out with a neuron of 16, epochs of 40, dropout rate of 0.2, and a batch size of 200. Our baseline actually did better than the random search. More on that later in the slide. And then for our second method, we use the support vector regression model. That was to plot and predict the longitude and latitude as the x, and then the magnitude as the y.
Now for the results of the neural network models. From the graph and the verbose of fitting the data into our model, it appears that the hyperparameter tuned model is underfitting the training data. We can see the intersection of the two accuracy values in the graph. The training accuracy is higher than the validation accuracy, and with an accuracy of 0.08, it is quite an inaccurate model. Perhaps if we tried implementing our model with more epochs, it would combat the underfitting of the training data. In comparison, the baseline neural network performed much better with a 0.91 accuracy. Overall, the base neural network model was the better performer out of the two models. Had we been able to do a grid search to find the best hyperparameters, the results may have been different. However, that would be too computationally expensive. The reason our baseline model did better was most likely due to the fact that the custom parameters that we chose for the hyperparameter tuning were not optimal to begin with.
So here are the results of our support vector regression model. On the far left, you can see we have the original data plotted as shown in the earlier parts of this slide. And then in the middle, we have the graph based on the predicted data. And to the naked eye, they look pretty similar. And then to the far right here, we have the original graph and the predicted graph and the differences. And you can see some smaller pink purple points there. Those are our differences. So there's some outliers that our predicted graph did not get. And below we have our R-squared, or correlation, pretty high correlation, and then a okay mean squared error.
So how can we improve our project based on what we've learned throughout the process? We can divide the problem into data and time. So for the data part, more data is definitely better. Our dataset collects the earthquakes from September 25th, 2022 to December 5th, 2022. The dataset was small, and might because of seasonal effects on tectonic features, the data isn't representative enough as well. With more processing power, we could use larger datasets for a more generalized picture. On the time perspective, one major limitation was because of the processing power, which limits the model and the fine-tuning algorithms we can use for this project. Because of the processing power and the numbers of the hyperparameters we wanted to test out, it takes too long for us to utilize a grid search CV in order to find a better hyperparameters than purely using randomized search CV. So that's the end of our presentation. Thank you for spending your time watching and listening.